Okay, so we're going to think about first, basically all of the fluid stuff we do divides into two categories. There's when the fluid is not moving and when the fluid is flowing. Okay, so we're starting with a liquid that is not flowing. Okay, so the word for that is hydrostatics, which you can probably guess what the root of that is, right? Fighting the snake with his head and it stopped moving because Medusa came or something like that. Let's see, so what we need is a big cylinder of water. Okay, we're going to think about a big cylinder of water. Oh, I'm sorry, that was hydrostatics. Like that. That's a cylinder of water. Can you explain the physics behind the red cello cup crushing? Oh, I was supposed to draw it. You see, when I deviate from my notes, right? It's red cello cup. Pressure, atmosphere. Put on the lid like that. Seal it up. Put it in the liquid nitrogen. And what happens now, the temperature goes down, which means the molecules don't move as fast. See how fast they were moving before? Now they slowed down. You can barely see that they're moving. And when they go slow, they don't apply as much force. So the net force was this way, right? And it crushed the cup. That was the idea. That's more fun than this, so thank you for asking. Okay, so now we have water in here. Now whenever I draw a water surface, I put the little waves on it. But that's just like figurative, okay? That's to let you know that's a water surface. We're doing hydrostatics, so there's no actual waves on the surface, okay? Sometimes I draw fish also, but there's no actual fish, okay? So let's think, what is the pressure above the water? It's atmospheric pressure. So I'll often write ATM like that to remind you that this water is in contact with gas, the room air gas, and gas remains constant in pressure. It doesn't care about the depth stuff we're about to do. So that's why we say, okay, it's just ATM, atmosphere there. And what we want to think about is a cylinder of water in the beaker. What? A cylinder of water in the beaker. So it's an imaginary cylinder. Okay, it's not real, but it's just we think of, here's a little volume of water, like this, like that. Has an area underneath there, A. Okay, so it's not the side area, it's that area, like that. And it has a depth D, so we're going down to D here. We're probing what's happening in the water at depth D, all the way down. Can you explain the physics? Okay. So it's an imaginary cylinder. It's an imaginary shape. Okay. Well, let's see. Cylinder of water in a beaker. Imaginary. And everything is static. Okay. So what we want to do is calculate the hydrostatic pressure at depth D. That's what we're about to calculate. We call it the hydrostatic pressure at depth D. So depth means how far down from the surface. Right? So that's why I drew it this way. There's the surface. We know it's an atmosphere, straight down. All right. Well, what we got to do is make a y-axis and say, well, if it's static, we got to go back to kinematics, back to Newton's second law, and say if it's static, then some of the forces in the y will be zero. Static. Right? Some of the forces of the y on what? Well, on this mass of water. Okay? So let's think, let's do a free body diagram. A free body diagram of that water column. Right, there it is. Well, we know mg is pulling it down, always. Right? And what else we know? We know there's some pressure on the top pushing it down. So I would draw that vector down and say that's P top times the area. It's basically our definition of pressure. The force from a pressure is just the pressure times the area. So we're not getting deep into the vectors and j hat and all that. We're just going to draw it down. Now what about the pressure down here? It's pushing up. So that would be P bottom times A. So we got the pressure at the top, pressure at the bottom. We got the weight. That's the only forces. Okay? And we did the negative sign in our head, if you don't see it. Right? When I said the P pressure top is down, the area vector would be considered up. That's out. Right? That would be A. So to make it down, we had to think about that negative sign. But we just did it intuitively. We said, oh, it's pushing it down. That's what that negative is about. So if you just intuitively could tell that here it's getting pushed down and here it's getting pushed up, you're in good shape. Okay? Okay, so sum of the forces is 0. So we say, let's see, this is negative P top times the area. This is minus mg, and this is plus P bottom times the area equals 0. So here we just treated it like just an object, just a column floating in space, and these are the pressures. But now we can relate them to actual pressures in the problem. Right? What is P top? Atmospheric pressure. Right? So a surface right at the top just feels the atmosphere. So this is minus P atmosphere times A. And what is P bottom is just P. We're trying to find the hydrostatic pressure at a depth P, or at a depth D. Oh, that's just P. Right? That's what we're looking for. So we plug those in. And then what about mg? That's the weight. We want to express that in terms of properties of the fluid that we've been learning about. All right, so we want to express that in terms of density. Minus rho. See my rho? See, that's a rho. And what do you multiply rho by? To get mass by the volume. Right? Rho times volume equals mass. That was in the definition of density. You got to keep up. But how are we going to get the volume of this column based on things we were given? It's D times A. Rho D times A. And are we through? No, we've got to write down the G. There we go. Those equal 0. PA, of course. There we go. So the A is going to cancel. A. And we're going to solve for P. And we're going to get the hydrostatic equation. We're going to get that the pressure at some depth equals the pressure atmospheric at the top plus, we brought this over positive, plus rho dg. The density times the depth times g. All right, and we'll talk about how to use it and what else the atmospheric pressure can be in a minute. Why does P bottom equal P? So we're just looking for this. The problem said find the hydrostatic pressure at depth D. So that's what we're just looking for. We're looking for P. I called it P bottom just to be more physical, but it's just P. Okay, let's stop for 5 minutes. All right, let's keep going. I've got a few good questions here. So the first good question is, what is rho? Oh, somebody was late to class, so we defined rho at the beginning. Rho is the mass density of the fluid, the mass per unit volume. That's what rho is. I will try to write my rhos clearly. Is it always towards the bottom? And I know who it might be. My phone can figure out who you are. Is it always towards the bottom? Come ask after class. I got to know which force you're talking about. Are you going to give us points back for true-false question in homework 6? I don't remember that far back. But seriously, if there was some homework and I said I'd fix it and then I never did, just email me and you'll be in a very long queue of emails and I will get to them all before we assign grades, I swear to God. Right? Or if there's one you're like, when I was studying, I accidentally redid it and it took away the point, just email me. I don't mind changing them. It's just, it takes me time. But this one I don't remember exactly what you mean. When will Predge problem 2 solutions be posted? Oh, soon. So we're pretty soon. I mean, definitely in time to study. Probably this week. We just want to make sure everybody turned it in. All right. Okay. So here we were. We have the hydrostatic pressure equation. So let's just enjoy this equation for a minute. Oh, look at it. Look at how beautiful it is. But remember what it's for. If you have a fluid anywhere sitting around and you want to know what's the pressure at some depth in the fluid, this is the equation. Right? If it's just sitting, it's static, it's just sitting there. However deep you go, you can always use this equation. Right? This will be the pressure at some depth D. The only thing that might be slightly different is what if you're on Mars and it's not 14.7 pounds per square inch and it's like 1. You would put a different PATM here, right? So often you'll see it written with this as just P naught. Right? We don't want to say this only works when it's exposed to atmosphere. It works when it's exposed to anything. It doesn't have to be on the atmosphere. Most problems have something open to the atmosphere. I'll tell you why when we do a problem. But technically, the book writes that as P naught. So P naught, PATM. If it's atmosphere, it's ATM. Are the next 3 lectures not on the test? Oh, my God. And then the person clarified, does the pressure have a direction? No, pressure does not have a direction. It's a scalar. It does not have a direction. Self-identifying. Who was late to class? All right. Or slept a little bit. I understand. I should be more spastic and keep you awake better. Let's see. Okay, so now what we're going to do is we're going to use this equation in a bunch of problems and to write a law. What if P naught was 0? Yeah, P naught could be 0. That's fine. You could have a vacuum. We'll do that later. Okay,